Okay, so it's time to talk about infinity. I guess I gotta share my screen. Yeah. To infinity and beyond and beyond and beyond. Um, yeah. Disclosure, I'm not a set theorist, so um, this may not be the most accurate depiction of all of these things, but these are uh versions of these facts that as I've come to learn to understand them. I made my hair as messy as possible. Sweet. Okay. So I'm going to remind you about some basic set theory, some facts about working with infinities, ordinals, cardinals, numbers, stuff you can do with them. Then I'm going to talk a bit about large cardinal axioms a little bit. Yeah, so basic axioms of ZFC. For those of you who watched my recent axiom of choice video, I went more into detail about this uh, recently. Um, but we've got basic things that allow us to build new sets from old. We can take unions, we can make sets of pairs of stuff. If I have a set, I can form the power set. I've got a thing that avoids Russell's paradox, and so on. How do we define numbers in set theory? Well, there's different ways to do it. There's various different approaches. But one possible way is, well, so this is supposed to be a mathematical foundation for everything. So everything's got to be a set. So that means even numbers have to be sets. So how should we define the number zero? I'll define it to be the empty set, right? Makes sense if we define numbers to, correspond to our intuitive notion of how many elements a set has. Of course, we haven't defined what it means, like what a number of elements is even. So we don't want to be circular, but yeah, so okay. First one's a empty set, then one is the set containing the empty set, so on and so forth. The general pattern being that if you've defined n, we define n plus one to be n union n. And you can prove that this process will never terminate, that you'll always get a new set from this. So you can prove that there's infinitely many sets. However, what you can't prove just from the sort of basic axioms we've talked about alone is you can't prove that there exists a set which contains all of these things, or rather that you can't prove that there exists a set that contains an infinite amount of things. Um, so you can prove there's infinitely many sets, but that's not the same as saying that you can collect infinitely many things together and form a set with infinitely many things in it. So we need an axiom that does that. It's called the axiom of infinity. Okay, yeah, we say, here's a formal definition of what it means to be an inductive set. I think I have some very old videos on set theory. You can watch those if you want more details. But yeah, basically, more or less, it just allows us to say that the set of natural numbers exists. We can construct an infinite set. Great. So we have this notion of cardinality, right? We say two sets have the same cardinality, or we say size if there's a bijection between them. So, we've got each of our finite sets, 0, 1, 2, and so on. And then Aleph null we denote as being the cardinality of the natural numbers. Or rather, I mean, we really we define Aleph null to be the natural number. So we sort of choose it as a representative of that equivalence class of bijections of sets. And so there's a whole arithmetic you can do on cardinal numbers. We can basically define products using Cartesian products, sums using, I guess, disjoint unions, exponents, basically through function sets, things like this. And they obey all of these sort of normal rules of arithmetic, right? Yeah, okay, I'll make this point later. But yeah, so we have some weird things though, possibly. Aleph null plus Aleph null, you get Aleph null again. Again, multiplication doesn't bring you any higher. So what do you have to do? Sort of these obvious things you would think of that at least for finite numbers, increase the cardinality. Well, we need something a little more drastic. That's where the power set axiom comes in. And it says that, the power set axiom allows us to construct power sets, and then we have a theorem that says the power set of any set has greater cardinality. It says a typo, there should be cardinality bars around the PA there. So we've got Aleph to the Aleph null, which is the cardinality, another way to express the cardinality of the power set of the natural numbers. 2 to the 2 to the Aleph null is the cardinality of the power set of natural numbers, and so on and so forth. Okay, so we can make bigger and bigger sizes of infinity. Great. Uh, how do we but is this all of them? Like, do we just keep going forever for that with that procedure? Clearly the procedure doesn't bottom out, but like, is it possible that that has some sort of limit? Or is there anything in between? Uh, well, this is independent of ZFC. This is known as the continuum hypothesis. It asks the question whether or not there's a cardinal number in between those. And so you'll remember this meme I used last time for the axiom of choice talk, but as too lazy to label for this talk. Except instead of having a maybe on the left is believing in the continuum hypothesis, so saying there's no cardinal numbers in between, and then just saying, oh, there is a cardinal in between. Actually, there's a whole infinite array. Like it can fail as badly as you can possibly imagine. If you look up, there's some Stack Exchange posts. There's a little more details about like, oh, there's certain numbers, certain amounts of cardinals that you can't squish in between, but like other than these few exceptions, you can just like it can fail as miserably as possible. Like there can be tons and tons, different kinds of infinities between the cardinality of the natural numbers in its power set. So you kind of get to choose. Yeah. Um, Also, here's kind of a jarring fact, speaking of the axiom of choice. So if you believe in the axiom of choice, you can choose a representative for every cardinal. But if you don't, then yeah, not only is that not necessarily possible, but you can have incomparable cardinals. So you can be handed two sets and it can be impossible for you to tell which one is larger. In fact, you can't even prove that the natural numbers, even though we think of it as the smallest um, natural number, you can't actually prove that it uh, injects into all other infinite cardinals. Wild stuff. Wild stuff. What can I say? Yeah, okay, so that's the basics of cardinal numbers. There's also these things called ordinal numbers. So what do we got for ordinal numbers? So we basically take this idea where for finite numbers for our finite cardinals, we said that alpha plus one, we'll just define that to be the union of alpha and the set containing alpha. So we might wonder, well, if what's infinity plus one, right? We take our first infinity, it's a set of natural numbers. What's infinity plus one in this case? Well, it would just be omega union the set containing omega. And yeah, it's then this sort of strange ordered set. So cool. We can count past another way. Of course, in as ordinal numbers, we say omega and omega plus one are different. But in terms of cardinality, they have the same cardinality. But we can keep playing this game actually, and we can define like higher arithmetic rules for these ordinal numbers. So I've written out here the example of omega plus omega. Okay, there's a technical definition, right? A set is an ordinal if it's transitive. So that says if x is an element of y and y is an element of alpha, then x is also an element of alpha. So you can convince yourself that this is true of all the our definition for the natural numbers. You can convince yourself that's true of all of those sets, and for example, of the all of the sets I have here, right? So okay, I put a little example um, down there, unpacking the definition of the number two, for example, and saying, oh, zero is an element of one, one's an element of two, etc. And there's all of these. Okay, I haven't explained all of these things very well, but so the point is I just want to make that we have all of these um ordinal operations of arithmetic, and there's sort of a well-defined procedure there. It's a little more delicate, right? Because this no longer corresponds to cardinality, right? So we've got to do some sort of things with suprema and the fact that these are ordered sets. So in fact, all of these things like omega squared, omega to the power of omega, and then this sort of supremum of all of these power towers of omegas, these are all actually countable still. So they're definitely these crazy different versions of infinity with their own arithmetic, but in terms of cardinality, these are all countable. But of course, there's a rich and varied sort of theory of arithmetic with these numbers. Anyways, but they allow us to there is more of a relationship going on with ordinals and cardinal numbers. So the Hartog's number of an ordinal, so this is just the smallest ordinal. So given a set, the Hartog's number of that set is the smallest ordinal that is not in bijection with any subset of A. So we're gonna look at an example on the next slide if this slide is confusing you. But so we'll define omega naught to be omega. We'll define omega alpha plus one to be the Hartog's number of omega alpha. And then if omega alpha is not what we would call or sorry, if alpha is not what we would call a successor ordinal. So there's definitions I'm neglecting for the sake of time, but basically that means if alpha is not the plus one of some other ordinal, then we basically define it to be the supremum of all of these ordinals that are less than it. So for example, the ordinal omega itself is not a successor ordinal, right? It's sort of this limit of all the finite ordinals. It's not itself the plus one of an ordinal. And then the idea is that we can associate aleph. So aleph, we define aleph sub alpha to be omega alpha. So these ordinal numbers, indexed by other ordinal numbers, give us different ways of articulating different kinds of infinity. And the generalized continuum hypothesis is the statement. So for example, the continuum hypothesis, an alternative formulation of it is to make the claim that Aleph sub 1 is equal to 2 to the Aleph sub 0. So the generalized continuum hypothesis then makes the claim that for every ordinal, this would be true. So if we go back to this question of like what lies in between the infinities you can build with the power set, um, again, just all sorts of craziness at every level, at every jump between power sets. In general, there could be all sorts of craziness. But the generalized continuum hypothesis, basically you say, no, I'm going to uh, I'm going to assume that there aren't any crazy things like that. And again, this is independent of ZFC, so you can choose to believe it fails as you could add an axiom that it fails as terribly as you like, or you can add the axiom that it holds. Yeah, totally up to you. And then we'll see, we already have this nice theorem highlighted here, that every ordinal has this nice expansion in terms of omega. So that's kind of cool, even though like there's this very general definition of ordinal is just a transitive set that's I forgot to say out loud, um well ordered by the membership relation. And do we assume the empty set to be in there? I don't know if we need that assumption or not, but that's kind of a very general thing, and yet, just like how all real numbers have like a base 10 representation, all ordinals have a base omega representation. Of course, these other the things in the exponents themselves, those can be all sort of wacky, wild um, ordinals of all sorts of crazy kinds, but still somehow it's like base omega. So it's kind of cool. So one of the reasons I wanted to point out this theorem, though, is that, well, let's think about what do we do with finite numbers? We constructed all these finite numbers, these finite sets. And we said to ourselves, oh, well, you know what? They satisfy a bunch of like nice arithmetic rules. It's really tempting to want to collect those all together into a set, and talk about this set as like an algebraic sort of structure, right? The set of natural numbers, or, you know, extending that slightly, the set of integers. So in the same way, we've seen both that ordinals and cardinals have these really great arithmetic properties, and it's entirely like the exact same argument applies. Like if you feel like you should be able to collect all of the finite sets together into one set and consider that as an algebraic structure, you should also feel that we should be able to do the same thing with ordinals and cardinals. But that goes beyond ZFC. That's, you know, we would possible, like if the set of all of these things was itself a set without any other qualifying statements here, then, you know, we're getting the set of all sets problems, and, you know, our axiom schema of comprehension forbids this, right? But oh, I thought I was going to make a point here. Yeah. So okay, maybe I'll loop back, maybe I'll loop back around to this. Let me jump to over to this slide for a second. One of the ways we can sort of work around this, and I'm going to give another argument in a second why this should be true, is we can suppose the existence of a new set, kappa, and we can consider the collection of all ordinals that are less than kappa. But we're going to assume something about this kappa. We're going to assume that the collection of sets of this kappa satisfies all of the axioms of ZFC. So therefore, this believing in the existence of this kappa, like this inherently goes beyond ZFC. It's a stronger assumption. So there's a couple different ways to think about what this is called. So this is an example of a strongly inaccessible cardinal. So there's two definitions that I like more than the stuff I've put on these two slides that I'm again not as comfortable with. I'm just not a set theorist. But one way you can think about it is an inaccessible cardinal is one which you cannot reach by doing power set operations, right? We asked this question about, is there some limit to doing the power set operations? An inaccessible cardinal is something that, yeah, you keep doing power set operations, you'll never reach it, right? So that's why it's like inaccessible by the ordinary operations you can do in set theory. Or another way to define it is it's a some cardinal number such that the collection of all sets with cardinality less than that number is a model for ZFC. Now again, now that collection a priori of all sets of cardinality less than kappa, that's not a set in the sort of strict regular way of thinking about things. But if we now assume this new axiom and we say, oh, there is a set with this property, there is a set kappa with this property, and we suppose it's a set, now we can form what we would call the collection of all kappa small sets. So that's the collection of all sets. Um, or now I can say it's a set of all sets whose cardinality is strictly less than kappa. And so now this allows us to create a universe in which that whole family of sets is itself a set. And that is strong enough so that we can talk about the family of all like kappa small ordinals and kappa small cardinals. And now we can view that thing as a set. We're not going beyond and having to talk about classes um, in our theory. And you might say, well, who cares, right? But I mean, for me, I think this is just slightly preferable because, like, okay, maybe we talk about proper classes. That's still technically going beyond like ZFC set theory, right? So either way, if you want to talk about these large collections of things, you're going beyond ZFC set theory. It's just if you make a large cardinal assumption, then you're still calling it a set, at least. And so it's still, instead of, oh, now you have to introduce this other concept called the class, and it has its own like axioms and stuff. So, okay, that's why I think it's slightly preferable. But there are these uh definitions. Okay, yeah, I don't need, I'm not an expert on this. I don't want to get into the weeds about the singular cardinals and regular cardinals and the difference between weakly inaccessible and strongly inaccessible, which like goes away if you make certain assumptions, maybe about the generalized continuum hypothesis. Uh, I'm sure someone who knows more will say something in the comments. Um, yeah, so here's one the ordinal and cardinal arithmetic stuff is sort of like one reason that you should believe in such a thing. And again, I think if you believe in collecting all the finite sets together in a set, this really isn't that much crazier of a thing. Um Here's another reason. Categorical foundations, right? In the modern mathematics, and even that modern, right? Like, I don't correct me if I'm wrong, but I think like categories for the working mathematician that was like from the published in the 60s or something, right? So and that was just when that book came out. I mean, for quite a long time now, mathematicians have been imagining ways to relate different, have been thinking about a language that relates different fields of mathematics. So, in particular, we like to think about categories and functors between these categories, right? If you don't know what all of these words mean, I mean, it's just to say that, okay, we study topological spaces, for example. But then it becomes very natural to think about the collection of all topological spaces, right? So if you're familiar with the concept of the fundamental group of a topological space, well, you can kind of view it as like a function of sorts that takes in topological spaces and spits out groups. So normally functions we think of as having a domain and a codomain. So it has some sort of set that it eats elements from and spits out elements into. So but now I mean all of these things are like they're too big to be sets in the ordinary ZFC theory. The collection of all groups it's not a set. Collection of all topological spaces is not a set, so on and etc. In fact, it's not even just this whole collection. Like if you just think about the collection of all one element sets, that's too big to be a set. So and that really feels like a thing that you should be able to gather up as a single collection. So, here's actually another reason to believe in the existence of an inaccessible cardinal. Because again, like, yeah, most people, the way we teach category theory and stuff, most people are happy to just, you take, um, you just say, okay, well then there's these things called proper classes, and I don't know what a proper class is. Like none of these, I don't think I've ever seen in a category theory book. They're like, oh yeah, we assume this is a proper class, but like, how many people actually like went through and looked at the axioms of like what a proper class is, right? No one. Well, not no one, but you know what I mean. So again, either way, if you want to do category theory, which is now indispensable for modern mathematics, you're going beyond ZFC. And so, well, you have two choices. You can either go beyond ZFC in a way in which you have to insert this new terminology of classes and like define that and learn about that. Or you can just add in this cardinality axiom, and and now you're still using the language of sets. So maybe it doesn't make a big difference, but I mean, I don't know. To me, I'm kind of sold on just, well, let's keep using this language. Um, but so maybe I've just convinced you that you should believe in one large cardinal. But what if you wanted to study the category of all? So one thing, a piece of terminology I haven't defined is we would call these. So you assume your yeah, sorry. Yeah, so we now might want to study like the category of all categories whose objects are allowed to be, as big as are allowed to be a set like on the order of kappa, right? Our inaccessible cardinal that we've posed. But now maybe you want to study the category of all those categories, because a category itself, like we also study, it's been very, very useful to study relationships between categories. And like, even of course there's category theorists now, but that's even a practical thing to study, like in homotopy theory, for example, or something like that. Or maybe you don't even care about that, but let's say you have two sort of categories whose classes of objects, or just take a category, the category of topological spaces, as classes of objects or topological spaces. You want to study functors from that category to itself. Well, now the whole collection of functors of that category, that's going to be even bigger than our inaccessible cardinal now. And functor categories are like super important. If you've heard of Yoneda's lemma, uh, like that is a super handy tool. But now we're talking about like, yeah, spaces of functors, and then that is now an even larger cardinality beyond the inaccessible one that we've posed. So you see the problem here. So there's this Grothendieck's universe axiom. And this actually, I had an existential crisis, but this is why the whole reason I started like investigating this topic in the first place was because like a year ago or so, I realized I was like, oh, all of this stuff I'm doing on a like daily basis, I'm using this language of sets, like I'm forming some growth and deep group of a category. But how do you actually say that that's a group and a well-defined thing? Like technically, even though at the end of the day I'm all getting like very normal set theory stuff, I'm somehow passing through an assumption of a large cardinal axiom. I started asking questions about this, and like it turns out, for example, SGA and EGA, which like a whole bunch of modern mathematics is based off of, it makes this assumption. It says for every cardinal, there's an inaccessible cardinal bigger than that. And you might go, whoa, okay, man, you convinced me to believe in one inaccessible cardinal, but a whole, for every one, there's a cardinal bigger than that. That seems like an insane axiom. Well, we can also there's maybe a more modest one. I cracked open this book on infinity categories recently. I don't understand a ton about them yet, but more than I used to. And it makes like a little bit more of a modest thing. It sort of it says there's just this countable chain of inaccessible cardinals, each larger than the last. So you can sort of take these stratified universes. of sets. And the thing is, like in practice, I don't think most mathematicians go beyond like kappa 4. Like even people who do category theory or infinity category theory, like correct me if I'm wrong. Someone correct me if I'm wrong. But like I think in practice, no one goes beyond kappa 4. But of course, you never know when we're gonna need to go one level deeper. May as well assume this infinite chain. So the question is, how much worse is this? Right? Because maybe I convinced you to believe in one inaccessible cardinal. Now I'm saying there's this whole what to consider an entire countable chain. Like how much stronger, how much further beyond ZFC? I mean, it seems like a lot. We're infinitely many more axioms, right? Um, as a side note, there's this really cool idea. Actually, I haven't seen this done with inaccessible cardinals, but I've seen this done in type theory. I have a video about a summer school I went to on homotopy type theory. And they do a cool thing there where there was one suggestion that actually you should imagine your universes are all indexed by rational numbers. Because what if one day you realize suddenly like you had one universe, you assumed one level higher, but maybe you realize all of a sudden that you needed a universe in between those two. So because the rational numbers are dense, you can always find one rational number in between those two, and so you can always sort of like slip a universe in between the two that you're talking about. I just think that's a cute idea. Um, yeah, okay. Is there some definition about hereditary small sets? Whatever. Let's not worry about it. Okay, so to say a little bit more about how crazy or not these large cardinal axioms are, we got to talk about the definition of a measure. So, a specifically, we're going to talk about a non-trivial probabilistic measure. Um, and the fourth assumptions may be beyond what most people would talk about in terms of probabilistic measure. But so it's going to be some way, it's some function from the power set of a set S. So we just want to find a way of sort of adding a way of describing the size of subsets of some set S, but we want it to land in the closed interval 0, 1. We ask that the entire set has size 1 and the empty set has size 0. Um, Makes sense, right? The parent set should be the biggest thing. The empty set should not count as anything. In ordinary, I mean, if you've seen measure theory before, right? If X is a subset of Y, then its size should not be counted as any bigger than Y. You can add sizes together at least in a countable way. I covered this up. The one thing that's different is for all X in S, I should have written we're gonna say that singleton sets also count as 0. Okay. Um, so then we say even more precisely, a measure is two valued if for every set, the every subset X of S, either it evaluates to 0 or it evaluates to 1. And then we get this, to me, a surprising result that an uncountable measurable cardinal, so this means if S is uncountable and you can find such a function on its power set, then S has to be uh, inaccessible. So that's crazy, right? That seems like this is kind of like a benign seeming thing to ask of a function, although you might already know that for the real numbers, well, it doesn't quite satisfy these properties, but like a very related question, you already know, assuming the axiom of choice, we can prove we can't do such a thing on the real numbers. But this leads us into a large cardinal axiom. So the answer to this question, if you can find such an uncountable two-valued measure, it already goes beyond ZFC, and again, like in a consistent way. Actually, I don't know what theorems we have about consistency. We definitely know it's not provable within ZFC. More on that in a second, though. Maybe I will come back to that. So let me just say that you can see from this list I just grabbed on the from the internet here. So right in the middle here, we've got measurable cardinals. And somewhere, oh, I didn't mean to do that yet. So somewhere, so here's like inaccessible. So down here at the very bottom of this huge list, is just the assumption that you have one inaccessible cardinal. Um, and then there's also so there's this thing called Malo cardinals. I don't even know the definition of them. I almost have my head around it, but they satisfy. So there's this question, right? I said, okay, well, let's believe in a countable list of inaccessible cardinals. A Malo cardinal. So if you believe in that list, and then you still took one sort of like beyond that, well, that cardinal would only have a countable number of inaccessible cardinals, um, like ordered less than it, right? And you could ask, well, what about, what if you assumed more and more cardinals that you had, chains of inaccessible cardinals? But what if there's an uncountable chain of inaccessible cardinals in that? So it turns out that a Malo cardinal has the property that the cardinals that you have this chain of cardinals that are less than that itself the length of that chain is inaccessible. So that's nuts, right? I mean, to me that's nuts. Like that's big. But like Malo, like the smallest like Malo cardinal is like down here somewhere, I think. Like it's less than measurable. uh um, so it seems like measurable cardinals arise from a pretty basic question. And like those are already like crazy larger than Malo cardinals. And Malo cardinals are like so incredibly larger than just like our countable collection of large cardinal axioms. But here's the whole thing, like this list is a list, an inexhaustive list of large cardinal axioms that set theorists study and are interested in. As you can see, yeah, measurable's not like it's not even like halfway up that list, right? So in the grand scheme of things that set theorists study, measurable isn't even that crazy, let alone these other uh um let alone our countable chain of inaccessible cardinals. There's this other thing. Yeah, I probably shouldn't even get into this as well because I'm not an expert on it, but more or less, there's just these um, V equals L is just sort of this assumption about how we can sort of define sets in stages. And well, V and L are sort of two different ways. So V is like these, if you've seen before, like the von Neumann universes and whatnot. And then L refers to this constructible universe where we just add this extra stipulation about how we're like about the formulas we quantify over at each step. Okay, I'll let I don't know someone with more expertise explain it to you in a PDF or something. Go look it up. But I just wanted to point out something that is interesting. So if this assumption that all sets are constructible is it holds again beyond ZFC, so if you just assume it's true, then the generalized continuum hypothesis holds, the axiom of choice holds, and in fact, you sort of lose these measurable cardinals. Um, but so I was confused at first as to, I'm just going to turn a light on. So I heard that set theorists tend to not like to use this axiom, this V equals L axiom, which I was a little surprised by because I was like, well, okay, I've convinced myself that all mathematicians should believe in a bunch of large cardinal axioms, but I was still thinking, as a run-of-the-mill mathematician, perhaps. I was like, okay, foundations, we want to make, conservative foundations. We want to assume as little as possible, improve what we can from that. So, V equals L, okay, the generalized continuum hypothesis seems nice. The axiom of choice seems nice. So, hey, if you have this axiom that implies both of those, and sort of kills off, obscenely large cardinals. That seems cool to me. Why wouldn't set theorists not be interested in it? Well, the sort of interesting thing is, I was talking to some people in a set theory Discord, and I mean, part of the thing is, so let me go back to this list. People people obviously study and are very interested in all of these crazy things. And this goes back to the consistency comment on measurable cardinals. So I don't know what's known about consistency, but these set theorists I was talking to were saying that, well, if you look at like these measurable cardinal axioms, like things do seem to be consistent. Like no one's found anything crazy yet. And there's all of these like very nice um, structure theorems. Things tend to like behave really well if you believe in the existence of measurable cardinals. So it's just it's like any other axiom, like the axiom of choice we've debated. It's like we have a really rich and interesting theory with these axioms. People enjoy studying them. And, it seems to be consistent with our base axioms anyways. And hey, I mean, yeah, I think there's no avoiding at this point large cardinal axioms. I think you got to believe in like the growth and Deak universe axiom in modern mathematics. I'd be willing to bet that some math, like technically, even though it may not strictly depend on it, secretly has that assumption if you go like trace your references back to SGA or EGA or something. Um, so so I think that's basically it, what I wanted to say on large cardinals. Yeah, the punchline is uh you better believe in a whole infinite hierarchy of large cardinal axioms. And I think it's not so bad. I think I've convinced myself that it's like not so much crazier than believing in infinity in the first place. I'll let you pause. This is one of my favorite memes. I've shown it in a bunch of talks. But speaking of law of excluded middle, I'll let you pause this and go do some reading. Actually, someone in the axiom of choice comment section recently suggested me some reading on this topic. So find that comment. I'll find that comment. Let's do some reading, and we'll figure out the answer to all this stuff together.